the first thing that you should realize, like I said, this was a prior pre-response question. I mean, I kind of manipulated it and changed it just slightly, so it's not exactly the one that I saw. But as you can see here, we have two elements, Z and X there. They're in their elemental forms. They're monatomic, as you can see. They are both combining with oxygen, and 3 moles of oxygen at that. So oxygen we know is double bonded like that, and we have 3 moles of each one. So that part is going to be the same for both reactions. But over here, we're going to have 2 times our X is bonding to O, 3 of them there, and then this would be 2 times the Z bonding to the O. Okay, so if you can't, you know, this didn't come to you visually, you can always draw it out. But the specific data point that they gave us were the delta H's. All right, and we can see that they're both exothermic because they both have negative numbers there. But when I'm looking at it then, which bond is stronger? Okay, stronger bond strength here. I'm looking at bond energies or bond enthalpy. So I'm looking at my formula here, delta H reaction, sum of the bonds broken minus the sum of the bonds formed. And this is what they would want you to cite in your answer, is that particular equation. So if we're looking here of X versus Z, right? This is going to be the same for the bonds broken. Same here, right? Because all we're doing is breaking 3 double bond oxygens in the process of this reaction. Okay? And subtracting the bonds formed here. And we are getting basically what? 6 X to O bonds over here, and 6 Z to O bonds over here. The significance here, though, is looking at the delta H's. This one's negative 573 kilojoules per mole reaction. This one's negative 842 kilojoules per reaction. So if we're looking, I kind of wanted that to be blue to match my blue. Let's do that. 42. Just based off of the equation, the way that this is going to work here, that means if this is the same, this number has to be much larger, right, to generate negative 842. Has to be a much larger energy bonds formed here. So these bond enthalpies have to be larger. The Z to O has to be much larger to release more energy ultimately based off of this equation. So that general construct there of using it to your advantage to figure out the calculations. So here they give you delta H's and they're asking for the stronger bond. You would go straight to the bond enthalpy equation, bonds broken minus bonds formed, because then you're looking for the bond energies. And remember, bond energy is a measure of the strength of the bond. The higher the number, that means that's how much energy would have to be inputted in order to break that bond. So in order to explain it, this is what I put. Z to O is the stronger bond because it has a higher bond enthalpy. The bond enthalpy being broken in O2 are equal for both reactions, but the bond enthalpy form must be higher for Z to O to get a larger negative value when subtracting using this equation. Bonds broken minus bonds formed. Looking at transfer, heat transfer, and thermal equilibrium. All right. Changes in a substance properties or change in different substance requires an exchange of energy. So first learning target here, this applies to all 3 topics here, 6.3, 6.4, and 6.5. So calculating heat needed to warm or cool or phase change substances. You're going to be interpreting heating and cooling curves again through these calculations. Explain thermal equilibrium. Calculate using variables Q equals MCAT or Q equals NCAT. Explain the law of conservation of energy. Q lost is Q gained. That's going to establish the thermal equilibrium. Calculate molar enthalpy for a given reaction using the calorimetry data, which gives you the heat, and then you figure out the moles, and you can do heat per mole, and you'll get your delta H that way. That is, by the way, the fourth way to calculate delta H. And you will also use the calorimetry data to specifically look at specific systems, like heat of reaction would be general for just reactions, but you can have heat of solution, the dissolving process of like dissolving a salt. Molar heat of combustion, that would be a reaction that involves combustion, and then neutralization would be an acid-base reaction where you have the heat exchange. Now, when a system absorbs heat, its temperature increases. The temperature specifically is a measure of the average kinetic energy of the particles in the sample. So not all the particles are exactly moving at the same speed. It is an average speed. Some of them are moving slower, some of them are moving faster, some of them are like right in the middle. So average kinetic energy of the particles is equivalent to the temperature. Increase in temperature is directly proportional to the amount of heat absorbed. So the proportionality constant is called the heat capacity, or C. Units of C are joules per degree Celsius or joules per Kelvin. We can use either scale here, and you'll see them both as Kelvin or Celsius. Now, in general, the Q is going to be the heat capacity times the temperature change, but we do know that heat is also amount dependent, so we are eventually going to throw in either mass or moles so that you have an amount based to go off of. Now, the larger the heat capacity being studied, the smaller the temperature will rise for a given amount of heat. Like water has a very high specific heat or heat capacity. So in order for water to change its temperature, you have to absorb a ton of energy before it's actually going to increase. Or you have to release a lot of energy before water is going to cool down. All right, heat capacity of an object depends on its amount of matter. It's usually measured by mass, okay? So 100 or 200 grams of water requires twice as much heat to raise the temperature by 1 degree as does 100 grams of water. Extensive, remember here, talking about amount dependent. Heat capacity is also specific to the type of material. Heat capacities are for particular phases as well. So every type of matter, this is an intensive physical property, okay, similar to how density would be, is that it's going to have, you know, this amount of energy change per gram per degree Celsius. So 1,000 joules of heat will raise the temperature of 100 grams of sand 12 degrees, but it will only raise 100 grams of water 2.4 degrees because they have different heat capacities. The sand's heat capacity is much lower, so it doesn't take as much energy to change the temperature. All right, specific heat capacities. Over here, our table, this one's based off of 298 K, 25 degrees Celsius, as you can see, is its ability to absorb heat, and that's per 1 gram per 1 degree Celsius or 1 Kelvin. Now, Kelvin and Celsius are on the same scale, they're just a difference of 273, so you can raise 1 Kelvin as well as raise 1 degree Celsius. But this is the amount per gram per degree Celsius or per Kelvin. And as you notice over there, water in liquid form versus ice versus steam, they all have different specific heats because the phase of matter does matter. And if you look at the bottom of the chart, you'll see lots of the metals there, and they are less than 1. They have very low specific heats. That's because they absorb energy very quickly and change their temperature. Metals can conduct heat. You know this. They warm up very fast. That idea applies here. All right, so the variables are C, CP, or CS. You might see any of those. And joules per grams degree Celsius, if you're looking at the calories per grams degree Celsius, those are the typical units, although you might see it, like I said, in joules per grams Kelvin. It would be the same 1 increment temperature scale there. All right. Joules per gram degree Celsius, joules, no, calories per grams degrees Celsius. Yes. Now, just to remember here that, you know, oceans and bodies of water help moderate temperature because water has such a high specific heat capacity. So, for example, if you're looking at comparing Sacramento to San Francisco, Sacramento is inland, whereas San Francisco is on the coast. There is a lot of difference in the sway of the temperature during the day. So, San Francisco to Sacramento, there might be as much of an 18 degree swing, okay, in the summer for Sacramento than there is for San Francisco. Why? Because San Francisco has the ocean right next door, helps moderate the temperature. Another thing about oceans to realize too is why people don't like to go to the beach in June usually is because the water is really cold still. Usually takes at least a month and a half or so to warm up. Why? Because it needs to absorb all that energy before it becomes warm enough really to be tolerable for swimming. But that also means then you can still go to the beach all the way pretty much in most areas through October because the water is still really, really warm. Another thing, water is commonly used as coolants in a lot of our machinery, also our nuclear power plants, because it can absorb a lot of heat before it changes temperature. All right, now moving on to molar heat capacity. Molar heat capacity, of course, involves the amount to raise 1 mole of a substance 1 degree, represented by C or Cn, and of course referring to the idea of mole. That is the normal variable for mole. So you might see joules per mole degree Celsius, calorie per mole degree Celsius, joule per mole Kelvin. Basically, you're doing the same sort of calculations that you would do with Q equals MCAT, except for instead of using mass and grams, you're using moles, and specific heat is going to be put to you, the molar heat capacity given to you in moles. It's the same kind of calculation, just different units, basically, so what's going on there. All right, quantifying heat energy. Heat capacity is proportional to its mass and the specific heat of the material. So we calculate absorbed and released based off of those variables. We need the mass, the specific heat, and the temperature change. So this is where we would do Q equals MCAT. M is the mass here, C is the specific heat, and delta T is the temperature change. Remember, is final minus initial for temperature change. Final minus initial. Now, the only problem with these, of course, is which scenario you're given. You have to go based off of the units they give you to figure out how to calculate it and cancel out the units. And a lot of times they like to stick with, you know, mass and specific heat and change in temperature. All right, so for example, we have 42 grams of water heated from 15 to 30. Determine the heat absorbed in joules. And yes, usually they would give you the specific heat. You have it there on the table. We would want to use the specific heat of water. So in that case, it becomes Q equals MCAT. It really is just plug and chug. So you would do the 42 times the 4.184 joules per grams degree Celsius and times the temperature change. Now notice that the grams would cancel with the grams here, and the Celsius cancels with the Celsius. So you ultimately end up getting this answer in joules. Now the mass and the temperature, they both have 3 here, so we just round our joules to 3 in the end to get the final answer. So this is the basic Chem 1 problem from last year. How much do you need to input to raise the temperature of the water? Here we're raising it 15 degrees. 42 grams of water is not all that much. And so really, in the whole scheme of things, 2,640 joules is not that much energy either. But no, are your problems in AP going to be this easy? Probably not.
Do you want us to write out the units in the formula?
You don't have to. I just do to show everybody how they cancel.
Okay.
And that is the whole purpose of the specific heats, having the 3 different units in there, because it is a drive unit. You need to have it to cancel out the others.
Thank you.
Yes.
Oh, also, for this problem, are we supposed to know that it's going to be,
Okay, never mind.
Wait, is freezing point of water 0 degrees Celsius?
The freezing point, yes, is 0 degrees Celsius. The boiling point would be 100.
Okay. So
But if there was a phase change involved, they would give you that information. So you can safely assume there's no phase change involved here.
Okay.
All right, heating curve. So quick review, remember the slopes all have to do with the phases warming. They're increasing their kinetic energy, like the solid particles, as you increase the temperature, vibrate more. And then eventually they do reach the melting point. The melting point is indicated by the first plateau here, and the second plateau here indicates the boiling point. Okay, so you can always find that information off the graph, the melting and boiling points off of the heating curve. Now, they warm until they get to their phase change. And yes, like I said, that's going to be a little bit more complicated, where you are going to have to do some warming and some phase changing before it's all said and done. The gas warming over there is E, so you can increase the temperature of the gas. It's just the particles will move faster and they'll make more pressure in the container that they're in. Also, something to note here are our 2 plateaus. Our 2 plateaus have to do with the phase changing. The first plateau is melting. If you're heating it, it's melting. If you're cooling it, it would be freezing. The second plateau is vaporization. If you're heating it, if you're cooling it, then it would be condensation. But you can tell the melting and boiling points based off of where the plateaus are. The other thing to recall about this is the plateau for melting is always a lot shorter than the plateau for vaporization. That is because we're talking about only overcoming some of the forces to melt it so that the particles are free to move and have fluid flow in a liquid. Whereas if you're going from liquid to gas, you have to overcome all of the forces to make it a gas, because we assume gases have no forces between them. All right, so this also is in a prior set of notes, but I like this graph because it compares the heating to the cooling. The cooling is really just opposite of the heating, but also at each level it tells you where the kinetic energy is changing and where the potential energy is changing. So on the slopes, the kinetic energy is changing. If you're heating it, the kinetic energy is increasing. If you're cooling it, the kinetic energy is decreasing. On the plateaus, that is where your potential energy increases if you're heating it, because you're making the particles spread out. You're giving it new positions, more potential energy. If you're cooling it, you're solidifying and pushing them together and limiting their position, so that's why the potential energy would decrease, okay? And threw these back in there, just going back over the basics of solids, liquids, and gases and their characteristics. The one that a lot of people, of course, don't remember offhand is sublimation deposition. That's solid directly to gas, gas directly to solid. And yes, as we're talking about heats of fusion and heats of vaporization, they could give you a heat of sublimation or a heat of deposition, where you go directly between those two, okay? All right, so phase changes. Heat of vaporization, delta H vaporization. This is the amount of heat needed to change 1 mole of the substance from a liquid to a gas. Now, what you have to remember about the heat of vaporization number is it is also the same numerical value for condensation. It's just going the other direction. So heat of vaporization is endothermic. When you are condensing it, then it would be negative and it would be exothermic. But it is the same magnitude value here. The heat of fusion is for 1 mole of melting from solid to liquid. And or that same number would be for freezing, liquid to solid. But remember, freezing is exothermic in the nature of it, so it's just going to be released rather than absorbed. Same numerical values though. They would not be different. And in some of the problems in the problem set, you might have to go look in the text for these values because they are in the tables. So you would just need to check that out. Like here. Here, table of heat of vaporizations and heat of fusions for 4 specific compounds. So they will give you these values usually in the problems, and you don't have to like manufacture them. Specific heats, heat of vaporizations, heat of fusions will be given to you. Now, the general equation is Q equals moles times heat of vaporization or moles times heat of fusion. But in a lot of circumstances, they don't give you moles to start with. So it's just easier to set it up as a T-chart where you change it to moles and then you use the heat of fusion or vaporization as a conversion factor. So for example, we have 244 grams of ammonia. And we want to figure out how much is released when it's frozen. So before I can use my heat of fusion, because it's freezing, so I need that value, the first thing I need to do is change it to moles. So this is 17.04 grams equals 1 mole. Now I can use my heat of fusion number. I know it's heat of fusion because we're talking about freezing here. And you look at your chart and you find that ammonia is 5.66. That is kilojoules per mole. So if you notice, mole goes down here, then you can go to kilojoules up here. So you can do 5.66 kilojoules per mole. And it nicely sets it up that way so that things will cancel. And you can end up getting your kilojoules here. And it's like, I think it's 81, is that right? 81 kilojoules are released. So you can state that, it already says it in the problem that it's being released, so it's already telling you the direction. So we don't really have to indicate the negative sign. If they were asking for that when it's frozen, like how much heat is absorbed or released, then you would need to indicate that it's being released and that it's negative and or there. That is one way where they can just ask you for a certain amount of grams, you tell the heat. They could also give it to you backwards, right? Where they give you the heat and they want to know how much can be transformed from that heat, the phase change. So here we have calculate grams of liquid ethanol that would vaporize into a gas when 5,980 kilojoules of heat are absorbed. So we're starting with the heat in this case. That means I would put the kilojoules down here and the moles up here. Now it says we're what, vaporizing? So which number do we need? We need vaporization of ethanol right here, 38.6. So, oops, the 38.6 is going to go on the bottom now next to the kilojoules, and the 1 goes on the top. Then all you have to do is take your 1 mole of your ethanol and change it into grams of your ethanol. And I want to say this is 46.08, but I'm going to check it real quick. Anybody calculate molar mass? Yes, 46.08. And we can figure out our kilojoules. No, we can figure out our grams. Grams that can be vaporized from this amount of kilojoules. And it looks like 7,140 grams can be vaporized with this amount of heat. So this is in essence the phase change part of the program. Now, of course, what they do for AP level is they combine them, right? Combine them into one problem. Like using your heating curve, because they will start you down here at like, you know, -8 degrees and then ask how much heat that it takes to get you up here to 87 degrees, right? So if we were to calculate heat there, you have to warm it first, then you have to phase change it, then you have to warm it again. So it takes like 3 steps. So if you don't remember, on the slopes, you're going to do Q equals MCAT. On the plateaus, you would do the phase changing. We did do some problems like this last year in Chem 1. However, just so you know, this is something they easily ask in AP. Most of the time, I would say I don't see more than a 3-stepper, although I have worked problems where we start down here in A and work all the way up somewhere in E. That would take 5 steps in order to do that one and be quite long. These problems aren't particularly hard, but, okay, you just have to make sure you're doing each step separately. And if you aren't provided a heating curve, you could draw yourself a heating curve to help you map it out. So, for example, here we have how much energy needed to heat 23-gram piece of ice from -11 to liquid water at 49.50 degrees. Now notice you would be given this information. You're given the heats of fusion and vaporization. You're also given the specific heats in the solid, liquid, and gaseous form. So that information would be provided to you if you didn't already have that. Okay? So first things first here, starting down here at -11-ish, that means I have to warm it. So what equation would I use for that? Q equals MCAT. So this is the first day, so I call it Q1. And I would do an MCAT there. All right, so we have 23 grams of water. And since we're in the solid form, I would need to use this specific heat right here, the solid one, 2.078 grams, joules per grams degrees Celsius. And then you also have to watch your temperature change. Where are we starting? Where are we going? -11, but we're going to 0 because at 0, then it's going to start to melt. So, final temperature 0 minus a -11. That becomes plus. Then you end up getting your joules here. I believe it's 525.7 joules, if you round it correctly, for that particular one. So that's the first step here that we have to do, is we have to warm it to the melting point. Then we have to melt it. So now we have to do the second step, this part, melting. That's Q2. And that's going to involve which one? We need heat of fusion to melt. This one. We're going to need that. And we need the moles. So moles times heat of fusion. Okay, and we have the grams, so we can convert it to moles. So for Q2, we have 23 grams of our H2O. We can change that to moles real quickly. And then we can use our heat of fusion number, 6.01 kilojoules. Like so. So that's the second step. And that gives us, I think, 7.671 kilojoules. And yes, the first answer is in joules, this one's in kilojoules. We will have to convert one to the other at the end. But we're still not done, because we still have to warm it. We have to go all the way up here to like 49. So that's Q3, which is going to be an MCAT. So for Q3, the only difference here is that we're in liquid water form. So what is our specific heat? 4.184. And the temperatures are now different. We're starting at 0 and we're going to 49.5 minus 0. So this, of course, ends up giving us new number. And we get joules, right? That's our Q3. Now, I think it's easier just to convert the others to kilojoules so the number's not too outrageously large. In order to do that, what do you need to do? Divide by 1,000 joules, move it over 1, 2, 3, and then it becomes kilojoules. 1, 2, 3, and that becomes kilojoules. Now we have to only do what? Add them. Q1 plus Q2 plus Q3 gives you Q total. And once you do that, I believe it's 12.960 kilojoules. So that would be the total amount of heat needed to go from -11 to 49.5. There's a phase change in the middle. All that lovely, wonderful stuff here. Now, also you can check out in here, I've cleaned it up a little bit with looking like that. And also the steps are in here, so you can check that out. Convert kilojoules by dividing by 1,000 and add them up, ultimately getting your answer.